simplest construction for a symmetric key encryption scheme. This is actually known as the one-time pad. And this is very, very simple. Okay, so let me say that the message is k bits. Maybe I will use a different letter because k often stands for the key. So, let us say that the message is L bits. Okay, let my secret key be L bits also. Okay, so now both of us have the secret key. So, our protagonists in cryptography are typically called Alice and Bob. So, both of them have this secret key, and now if one person wants to send a message to the other, then the ciphertext is simply the message XOR the secret key. So, this is called a one time pad. It's for obvious reasons. So, how does decryption work? So, decryption will take the ciphertext and the secret key, and what will it do? It will simply compute ciphertext XOR secret key, which will simply give you the message back. Okay, so, this is the simplest crypto system. The disadvantage of course is that once you use the secret key, you have to just throw it away. I cannot use it again because let us say I am an attacker. Then if I see M1 XOR SK and I see M2 XOR SK, then I can simply XOR together these two ciphertexts and get M1 XOR M2, which is obviously a leakage, right. So, we said that we do not want the ciphertext to leak anything, it should be equivalent to not having the ciphertext. So, so that is the idea here. Okay. So, the secret key is one time. So, this is only one time use, but good, I like that you are trying to make the connection. So, this is the simplest construction. The obvious disadvantage is that the key has to be as long as the message and you have to throw it away. So, one might complain that if I have to meet and exchange a key and then I have to go back and use it up for a single message, I could have also just met and exchanged the message itself. The only advantage it offers is that maybe the message I get to know it later. So, a priori I can exchange the key and then later when I get the message I can use this. But the security that this gives is pretty amazing, right. So, the security is in fact perfect. So, basically in absence of the secret key, in absence of knowing anything about the secret key, what you see is a purely random string, right. So, your ciphertext is distributed perfectly uniformly and it is equally, every element in the message space is equally likely, right. So, the secrecy that you get is perfect. Unfortunately, there is a lower bound by Shannon which shows that the key length and this one time use is actually inherent. So, I cannot really do better if I want this kind of security. So, then obviously the next question is fine, I mean maybe I am okay with a weaker type of security. So, in that case what should I do? So, let me just try to sketch an outline. Okay. So, let me say that my secret key k, let us say that this is 100 bits. Okay. So, let us say that I have some message m. Here is what I would like to do, I would like to expand SK to I do not know 1000 bits, let us say. Okay, and let us say that my message m is only 10 bits or it can also be 100 bits. But if I can somehow expand my secret key, stretch it somehow, if I can stretch my secret key somehow while preserving its randomness, its random lookingness, it won't be random, right, because obviously I am stretching it. So, entropy will not, you can't magically create entropy, not classically in any case, right. So, suppose I could somehow expand this, then I do better than last time, right, because now I can encrypt 100 bits many times, right. Is it fine? So, now I have 1000 bit long key, right. So, I could use the first 100 bits for the first message, second 100 bits for the second message, and I could do this many times, right. So, the second step is that use the one time pad construction on only a part of the secret key. Okay, and the decryptor does the same thing. So, the decryptor can also do the same step 1, and the second step can be as in OTP. So, basically if I can somehow expand this secret key, then already this is very useful. This is giving me something much better than what I had before, and this is actually what these pseudo random generators do. So, the guarantee that they give is that if I have a random string of a certain length, then I can deterministically compute something on it, okay, so that of course if the attacker also has the starting point random string which we call the seed, then of course you cannot hope to fool this attacker, but if they do not have it, then somehow this stretching will work. You can prove based on the existence of one way functions alone that pseudo random generators exist, right, and you could also construct them directly using different mathematical assumptions. So, this would be something which is already better, and as I also just mentioned, I want to write this here. So, one way functions, right, these themselves imply these pseudo random generators. This particular scheme I showed you has a few limitations, like you have to remember which parts of the string you have used up already. If I further upgrade these PRGs to what are called pseudo random functions or PRFs, then even that limitation goes away and I get a genuinely good symmetric key encryption scheme. Okay. So, this is all stuff that we are not going to study in this class. I am just telling you for context that one way functions are a powerful enough object to give us symmetric key encryption. Okay, so that is already something quite useful. But now what about public key encryption? So, previously what we had was every pair of users has to agree on a secret key, right, but this is obviously problematic. That means that in this class, let us say if there are 25 of us or 30 of us, then I need roughly square of that number of keys to be generated, right, and in large systems this becomes a pretty big nightmare because key distribution is a problem, and then if I am talking to 500 people, I have to actually maintain 500 keys, right. So, this is a scalability issue. So, a very clever idea which was quite a revolutionary idea back in the 70s was can I have public key encryption. So, again now we are used to it, but I urge you to think about it completely afresh. This is really very surprising. What is the idea? I just have one public key and I just have one secret key. I publish my public key on the web page or I write it on the board or whatever it is. everybody's public key is disseminated everywhere, but everybody maintains a secret key which they keep secret. So now instead of hiding n different secret keys, I just have to hide one of them, okay. And when you want to send me a message, you just use my public key to encrypt the message, okay, and I will use my secret key to decrypt it. So obviously the public key and the secret key should be mathematically related somehow for this to work out. So what about public key encryption, right? So what do we need from can I build this using one-way functions? That's the question I want to ask. And indeed it is. So one-way functions don't suffice, okay. So what we need is invertibility, like you just pointed out, efficient computation, of course, like the forward direction should be efficient. It should be difficult to invert in general. So if the adversary sees the ciphertext, she should not be able to decrypt it, but it should be easy to invert given some kind of auxiliary information, some kind of secret information which we call a trapdoor, okay. So if I just have efficient to compute and difficult to invert, that is a one-way function. If I have those two plus invertibility, that is a one-way permutation, okay. And if I have all of these, sorry, the numbering is wrong here, if I have all four of these, then this is a trapdoor permutation, and here enters the star RSA. So RSA will give you a trapdoor permutation. And surprisingly, even though there are many encryption schemes from many assumptions, trapdoor permutations are in fact notoriously hard to find. So RSA is among the only assumptions that gives us this. So what I am saying, be careful here. So a trapdoor permutation does imply encryption, public key encryption, okay. But public key encryption could also be constructed using other mathematical assumptions. You do not have to use trapdoor permutations. However, RSA is a trapdoor, does give you a trapdoor permutation. We will see that. Okay, so public key encryption could be constructed from other assumptions which do not give you trapdoor permutations. Okay, so how to build public key encryption? So there are two routes. So you know, one is, as I said, you use a trapdoor permutation and you sort of build this PKE using that. So this is called the more complexity theoretic approach. So here you assume no structure on the underlying object. You just have a definition that there is a trapdoor permutation, that means it is invertible, it is one way, it is efficient to compute, it is efficient to invert given auxiliary info. You just have these definitions, you assume nothing else, and using a trapdoor permutation you build a public key encryption scheme. This will be on your next homework. It is not very hard. And the second approach is the more direct approach. So this is the more algebraic approach or number theoretic approach. So the advantage of the latter approach is that you are likely to get much more efficient constructions. The advantage of the former approach is that it helps you to understand where the hardness is coming from, right. So let's go to the next question which I had highlighted previously, right. So how much power does this adversary have? So now we will start writing things down more formally. So first let's look in the classical setting. So we will define like polynomial time. Okay, so this just means that we use, maybe I should write it more formally, let me do that. Okay, so if an algorithm A gets an input of size k, it is considered polytime if it runs in order k to the c steps, where c is a constant. Okay, and probabilistic polynomial time is as above, but algorithm can be randomized. Okay, so basically this algorithm A will now get some input and some randomness. Okay, so whatever is its output, this is a random variable, maybe this arrow might be confusing. So, this y is a random variable, right, because it depends on the underlying randomness. This is clear, and I mean you can also immediately see that there is a well defined notion of quantum polynomial time, right. So, now if I just generalize this definition to allow the algorithm to be quantum, then I get quantum polynomial time. So, here I need not model probabilistic separately, because quantum can include probabilistic within it. Okay, so now we look at another important concept. This is the concept of negligible functions. So, this is capturing probabilities that are too small for us to worry about, that is the intuition. Okay, so let us see how to define it. So, we say that a function Vk is negligible denoted by negligible k if for any c greater than 0 there exists a k prime such that for all k greater than equal to k prime, v of k is less than 1 over k to the c. So, basically this is saying that this function grows slower than the inverse of any polynomial. You fix any polynomial, so you fix any c, okay, then for large enough inputs this function will be smaller than 1 over that polynomial. Okay, the most common example, as I already said, is 1 over 2 to the k. Okay, and then I also want to talk a little bit about the security parameter. So, we already discussed this a little bit. Okay, so this is intuitively the size of the problem. So, you know this k that I am using above, right. So, what is the meaning of the security parameter? So, just as the name suggests, right, I can parameterize the security level of anything I construct. So, when I want to construct something, I do not want it to be married to a particular level of security, right. Depending on the application where I use it, I would like to change the level of security. So, if I already gave this example, right. So, for some very simple application, maybe k can be as small as I do not know 50 or 20, right. For another more important application it can be 100. For like a very important one, maybe it can be 150, 200, something like that. So the point is that the level of security changes changes depending on the application, and the security parameter captures that change. Okay. So why should I not always set it to be very high? So for a particular K, I want the probability of successful attack to be negligible in K. That is why I defined negligible just before this, right. So I want the probability to be negligible in K. So my question is, why can't I always choose K to be very large, you said, but the idea is correct. So the idea is that the honest algorithms, right, so the encryption algorithm, decryption algorithm, etc., these honest algorithms are probabilistic polynomial time in K. So you remember we defined probabilistic polynomial time, right. So here also there is a size of input, this is also K, right. So here this is input, let us say, is of size K. So there is a trade off. The honest algorithms run in time polynomial in K, right. So it is some K to the C running time, and the attacker's probability is 1 over super polynomial in K, right. So it is negligible in K. So if I make the attack probability to be smaller and smaller, my honest algorithms will become slower and slower. Everyone sees that? Yeah. So the honest algorithms their running time grows with K, right. So as you and this is intuitive, you expect that more security should be more expensive, right, you expect that. So the next thing that I wanted to discuss was, what are good values for K, right. So I already said that we have this security parameter. Let me just write here trade off so that everybody remembers. Okay. So we already said that the probability of our attacker winning So how to define the win of an attacker? This depends scheme to scheme, right. So for encryption, I will say that if it can distinguish between an encryption of M0 and M1, it wins. We will look at those definitions more formally, but whatever I define this winning condition to be, I want the probability to be negligible in K, right. Probability of attacker winning is negligible in K. Okay, so for example, let us take 1 over 2 to the K, right. So how small is 1 over 2 to the K, which is the same question as how big is 2 to the K. Okay, so there are some sort of interesting you can get a lot of interesting examples online. Okay, so one nice one that I read from freemars.org. I don't know what the website is about otherwise, but it gives this nice example. So suppose I take a sheet of paper. Okay, so let us say this sheet is infinitely big. I fold it, right, and then so I fold it like this, and then I fold it again, and then I fold it again, and I fold it again, and so on. So after doing this 100 times, how big is the stack or whatever, how thick is this folded paper. So according to this website, if I started with a sheet of paper 0.1 mm thickness, if I started with this, then after 100 iterations I get 13.4 billion light years height. Okay, so this is 2 to the 100. And you know, this 13.4 billion light years basically starting from where we are, this is beyond the edge of the universe. This is 2 to the 100. Okay, so 2 to the 150. So it's actually a little bit addictive to read you know, different numbers. It's quite fun. So 2 to the 150. Yeah. So if I have billions of supercomputers, let's take the biggest supercomputer that the world has. Okay, I would expect that China has it. Let's take that. Okay, if I have billions of those and they run for the entire age of the universe, then maybe they can do these many steps. Maybe. Okay, so billions of supercomputers running for the age of the universe. Maybe do these many steps. Okay, and 2 to the 240. This is the number of elementary particles. So not even dust particles, but the number of elementary particles in the observable universe. So anything bigger than this does not correspond to any quantity that we can count. Okay, so the reason I am showing this is because I would like to make this concrete. I mean, when we say that, you know, you can drive the error probability down to be exponentially small, this is the kind of guarantee it gives you, right? Basically, this will never happen. In this universe, a number bigger than this corresponds to nothing. It is an unphysical quantity, right? So that is how big these numbers are. Okay, and so now think about one-wayness. Let's see. So if I multiply two numbers of 200 bits each. Okay. Then how much time does this take? Very little time. Okay, less than a minute, I mean few seconds, something like that. So very little time. This is very fast. Okay. Now if I want to factor a 200 bit number, the best known algorithm for this runs in time to the 100, square root n, right? And 2 to the 100 is that number, this billions of supercomputers, you know, age of universe. So, look at what one-wayness is. This is one-wayness. So, it's really a gap. I mean, it's not, I like seeing these numbers because, you know, it shows you the power of the symbols. Okay, so this is one-wayness. But a quantum computer can solve this in a few minutes. I mean, I am saying few minutes, I have no idea. It is quantum polynomial time, but you know, since they have not been built, I think I can say few minutes because you know, it does not have to correspond to anything. Okay, so this is the power of one-wayness and this is also the power of quantum.